Okay, so yesterday we saw what is the expectation value of the over this later determinant in case we consider a one-body operator. Today, I just would like to discuss with you what happens when we consider a two-body operator, and let's say, in the problem we are discussing, that is the effect of the electron-electron interaction, the two-body operator that I will not use directly now, but will be the operator I will substitute at the end into the equations, is the operator that relates the interaction energy between two particles, two electrons that belong to the system. So in this case, we have that the value of the operator depends on the coordinates of two electrons. And since I will use this, what I'm going to say at the end of the calculation, as you notice here, as it happened yesterday, the actual value of the operator depends on the value of the coordinate. So depending on the value of Ri and Rj, then the value of the operator changes. But the structure of the operator does not depend on the coordinate. So if you replace Ri with Rk, then the structure is always the same. So this expression does not depend explicitly on the index of the coordinate. Due to that, we will be able to do, let's say, to generalize the result as we did yesterday for the one-body operator. So now the idea is to evaluate this term here. So as we did yesterday, we may write down the full expression of the slate determinants. We have the 1 divided by factorial n in front of the summation as a normalization factor. Then we have the one electron wave functions. Just for the first time, I write also the wave functions corresponding to I and j. Okay, in this case, we may observe that the operator, the two-body operator, if we fix the value of I and the value of j, that affects only these two wave functions. So these two on the left side and the other two on the right side that correspond to the index I and index A of the position vector corresponding to those two electrons. So for what concerns all the other indexes, so from 1 to I and then from I to j and to j, from j to n, what we have the same situation that we had yesterday. So in that case, the permutation P and the permutation Q has to be equal. So for, let's say, any arbitrary for any index that is different from I and different from j, then we have that P has to be equal to Q. So the two permutations has to be exactly the same over, for instance, index 1. Because just to make an example, if you notice here, we have R1 here R1 on the other side, the AJ, the two-body operator, does not affect the one coordinate. So when you make the scalar product, if P1 is different from Q1, you have 0. So this is the requirement in general for all the indexes apart from I and J. In this case, we have to consider that the number of indexes involved in this requirement is equal to n minus 2, because from n indexes, we just remove index I and index J. So we have an overall contribution that is equal to n minus 2 factorial from all the terms that come from this situation. And yeah, if you don't mind, I just remove this part here. I just write the latest down here to avoid the superposition of the equation I'm going to write in this sentence. So I just cancel here, and then I repeat everything below. Okay, so this is equal to n minus 2 factorial divided by n factorial. Okay, at this time we are left with, let's say, if we now consider Pi and Pj and Qi and Qj, at this moment we have that the P and Q permutation has to be equal apart from index I and index J. So the only choice we have is to decide what is the correspondence between I and Pi and J and Pj, and I and Qi and J and Qj. So due to the fact that these two permutations, P and Q, has to be exactly equal apart from two indexes, over those two indexes, we may not say that they have to be exactly the same. So at this moment, we have at least two opportunities. One opportunity is that P is equal to Q over those two indexes. So option one is Pi and Pj are exactly equal to Qi and Qj. The second opportunity is that Pi and Pj are that if you fix Pi and Pj, then Qi and Qj are exactly the same values but exchanged. So due to the fact that we have just, let's say, these 2 degrees of freedom concerning the value of the two permutations, then we may have that on those two values, the two permutations are or exactly the same or just an exchange. So at this point, the two possible solutions that we have at disposal are two solutions like this one here. So we have that if I consider coordinate Ri and Rj, now in place of writing P of I is as an effect any possible index for the corresponding to the I value. And to be general, I call K the value of Pi, and I call M the value of Pj. So Pi and Pj correspond to a permutation that associates to I and J two of all possible indexes in the system. So at this point, I call K and M the result of the application of permutation P to I and the result of permutation P to J, respectively. So one solution is the following. So the value of P over I and the value of P over J are exactly equal to the values of Q over I and the values of Q over J. So in this case, we have the same indexes. So K corresponding to Ri and M corresponding to Rj. At this point, we have a summation over over all the possible values of those two indexes, and we also have the 1/2 factor to avoid the double counting. Then the other solution is that if Pi corresponds to K and Pj corresponds to M, then Qi and Qj correspond to two values that are exactly the values corresponding to I and j, but exchanged. If you make an exchange, then we have to consider a minus sign in front of the permutation because we exchange the two values. So we have minus, I will write also the minus down here, phi k ri phi m rj, the two-body operator, and then we have phi m of ri times phi k of rj.
Excuse me, teacher, could I make a question, please?
Yeah.
It's not clear for me why we have the same indices for the both function, both at the left and right, k and m. My doubt is that k m are chosen as some indices from the permutation of I and j. But the permutation p and q, I suppose they're different permutations. So why do we use both km at left and right?
Because
I don't know if okay.
No, if I understood correctly, the question is why we suppose that the value of the two permutations have to be exactly the same. Sorry, why?
Yeah.
Okay, because over all the other indexes, the permutations have to be fixed, to be exactly the same permutation. So or let's say, just to make an example with a smaller number of indexes, if we have 1, 2, 3, 4, and 5, and we have to exchange those, let's suppose that I and j are 3 and 4. At this point, if the correspondence to, if in this case, all the other values are fixed because the permutation are fixed by the fact that we need to require that this scalar product is different from 0, then the only two values that are not involved by the permutation are I and j. So due to that, only, let's say, just two values are left for the choice of the final value of the effect of the permutation. So that's why I use the same values for k and m here, both here for p and here for q. Torna, posso ripetere in italiano o torna?
Sì, mi si è bloccato anche un po' l'audio in mezzo, quindi probabilmente mi sono perso anche qualcosa, per cui se non è un problema le chiedo se può ripetere, sì, grazie.
Sì, dico in italiano così magari riesco a esprimermi meglio. Diciamo, la condizione la richiesta di avere un prodotto scalare qui diverso da 0 per tutti gli indici che non sono i e j, facendo adesso un esempio con meno numeri, quindi faccio finta che la sommatoria vada solo su 5 valori, non su n che è molto grande. Quindi facciamo finta che i e j siano 3 e 4, tanto per fissare le idee. A questo punto 1, 2 e 5, chiedo scusa, la corrispondenza di 1, 2 e 5 con altri valori, che qui ho sbagliato a metterli uguali, quindi potrei avere tipo un 2 qui, un 5 qui e un 1 qui. A questo punto gli unici valori che rimangono fuori sono 2, quindi io ho fissato tutti gli altri, quindi i valori finali che mi rimangono a disposizione sono solo 2. Per quello ho scelto gli stessi 2 sia qui che qua, perché pur essendocene n, quindi un numero molto grande, il vincolo posto sulle altre mi blocca i valori finali anche solo su quei due indici. Per quello devo andare a pescare, diciamo, sempre dallo stesso set di numeri.
Ok, adesso va un po' meglio, sì, grazie.
Ok. Yeah, so at this point, we may, let's say something similar to what we said yesterday. This is the expectation value that we have for, sorry, I made a mistake. Please remove this, this one half. So yesterday we said, okay, this is the expectation value that we expect to have if we consider only one of the possible two-body operators. So it's just like as if we had fixed I and j in this expression, And so we are evaluating what is the effect of the, let's say, interaction operator that affects only electron I and electron J. Due to the fact that the structure of this two-body operator does not depend on the indexes, but just on the, let's say, here the structure is independent on I and J, depends just on their values, but nothing changes here if you remove I and J and put there N and L, for instance. Then in this expression, we may remove the explicit reference to the coordinates and just call Ri and Rj as R and R prime, because the final point is this expression depends on I and J because we started the calculation using I and J, but there is not a physical motivation to fix I and J because, again, the structure of the operator does not depend explicitly on those two indexes. So in this case, we may write this as n minus 2 factorial divided by n factorial gives us a 1 divided by n times n minus 1 in front of the summation. Then we have a sum over k and m of phi k r phi m r prime. And then just to remind that A in this case is a two-body operator, I just put the two label to A just to remember that that is a two-body operator. And then we have phi k r phi m r prime minus the same expression. So phi k r phi m r prime, again the two-body operator, and then phi m r phi k r prime. Yeah, before going on, I mean, I will make another comment later. Okay, so this is the result corresponding to just one operator. If you then want to obtain, let's say, the starting point of in the Hamiltonian was that the two-body operator, the full expression of the complete two-body operator was a summation over I and J, and here we have the 1/2 to avoid the double counting, where all those contributions coming from the interaction between the electron among the electrons in couples were included in this summation. Due to the fact that here the contribution, if you notice, the contribution of just one of those gives you this expression. But then, due to the fact that at this point we have not an explicit dependence on the coordinate, so there's not here an explicit dependence on I or on J, we may just say that if we want to replicate this summation here, then we may just sum up this term that we have obtained here for exactly the same amount of times. So we should write here, we should sum this. We have the same element for a number of times that is equal to the number of times that we use all the indexes here. And if you, let's say, if you choose one I at random, then you have at disposal n minus 1 values of J, and you may choose the initial value of I a number of times that is equal to n. So if you consider this and the amount of time you have this term here, you have exactly n times n minus 1 times this expression. So due to that, if we try to write this, we have 1/2 times n minus 1. What is found here? Because this is the number of operators we need to consider, and this is the result that corresponds to one of those operators, result that doesn't depend on the specific coordinate. So at the end, the n divided by, sorry, the n times n minus 1 that we have at the denominator in this expression disappears due to the n times n minus 1 factor that we have for the summation of the two indexes related to the description of the full expression that includes the contribution of the two-body operators relating to all the couples of electrons. So at the end, the expression we have is just this expression here with the two indexes, k and m, with the 1/2 in front. So if you notice, we started with the summation over the position indexes, because here the index runs over the position. We end up with a summation where the index doesn't run on the position, but runs on the level. Because here we have again the double summation, but the summation is on the index on the level, not on the coordinate of the electron. So I just change page and rewrite all the expressions so I can make a comment on that. So at the end, we have that the contribution of the two-body operator, so the 1/2 sum over I and j of E squared. So the expectation value of this operator over the Slater determinant. I just had something. I've always, let's say, I have in mind the fact that at the end I have to suppose to include this expression for the two-body operator. So what I called A up to now is E squared divided by the coordinates. So I have in mind that. I'm not writing that in the equation just to make the expression shorter, but for the moment, the operator that I have in mind is always the potential energy due to the interaction between the two electrons. So what we have here is 1/2 sum over m and k of phi m of r, phi k of r prime. Then let's introduce the actual expression of the operator, that is E squared divided by r minus r prime. And then we have phi m of r, phi k of r prime. And then we have minus phi m of r, phi k of r prime, E squared divided by r minus r prime. And then we have phi k of r, phi m of r prime. Yeah. So let's just now discuss what is the contribution of the first term, and then I will comment on the contribution of the second term. So let's first investigate the initial term. In this case, we have the phi m of r, phi k r prime, E squared divided by r minus r prime. Just one comment. In principle, I should write here the 1 divided by 4 pi 0 term, because for the moment we have, let's say, for the moment the let's say in a while we will also consider the contribution of all the charges included in the system to the dielectric constant of the system itself. But for the moment we have not made that calculation. So for the moment we are supposing that the interaction takes place like in vacuum. So here I should include the 1 divided by 4 pi 0. If you don't mind, here I just write this expression just to make the equation shorter. But please remember that we also need to take into consideration the 1 divided by 4 pi 0 term. And then to conclude the integral, we have phi m of r, phi k of r prime. If we write the expression corresponding to that, we have the integral, double integral over d3r and d3r prime. We have the conjugate of phi m of r, the conjugate of phi k of r prime. Then we have e squared divided by r minus r prime. Then we have phi m of r and phi k of r prime. And here we have that the coordinate r corresponds to phi m conjugate on this side and to phi m on the other side. So we may group the conjugate of the m level with the wave function corresponding to the m level, and just write the square modulus of phi m. So we have the integral over d3r and d3r prime of the square modulus of phi m. Just let me divide e squared into minus e times minus e. So this is square modulus of phi m times minus e. Then we have, for the same motivation, minus e times the square modulus of phi k r prime divided by r minus r prime. If you notice the structure of the numerator, this part here, so this part of the numerator, if you remember what we did when discussing the Hartree approach was to consider the not the interaction with the, let's say, point to point with the in between the electrons, but to discuss what happens if we consider the charge density associated to one electron, or in that case also to all the possible electrons. So in this part, the phi of m square modulus times minus e, you may consider that to be the charge density corresponding to the charge density corresponding to level m. And also here you have the equivalent of the charge density corresponding to level k. So this can be written in a slightly different way as in the integral over d3r prime of the charge density of level m in position r. Then we have the charge density of level k in position r prime divided by r minus r prime. So this is a sort of point-to-point interaction between the charge densities corresponding to the two levels. As we will see later, this is at the end will have an expression that is quite close to the expression that we obtained with the Hartree model. So the idea is that the first term of the in this equation, so this term here, gives a contribution that is, let's say, the contribution of the Coulombian interaction, the pure Coulombian interaction in between the electrons in the system. So this, at the end, when we make other steps in the calculation, will be very close to the Hartree result for what concerns the electron-electron interaction. So this represents what one expects to find when one considers the contribution of the interaction between the electrons. So again, the Coulombian contribution due to the presence of all the electrons in the system. And just to label this term, as this term was the term that was obtained when the values corresponding to I and j with permutation p were exactly equal to the values corresponding to the to I and j using permutation q, this term is generally called direct term. And another motivation behind the use of this name will be clear in a couple of minutes, because the other term is a term where if you associate to I and j a couple of values using permutation P, the values that you associate to the same indexes using permutation Q are exactly the same but exchanged. So this is called the exchange. So this is the exchange term, and the other one is called direct term. I would like to point out another thing that I never included in the equations because, and this is the spin component. If you remember, I told you that the full expression of the wave function should depend both on the position coordinate of the electron and on the spin coordinate of the electron. So in principle, when I replace when I write down in full expression this scalar product, I should also include the spin coordinate. So there should be a spin coordinate corresponding to m and the spin coordinate corresponding to k. In this case, if you notice, the scalar product is evaluated between the wave functions that correspond to the same coordinate, spatial coordinate, and also spin coordinate. So in this case, we have r here and r here. So level m is found both on this side, so on the non-conjugated side, and on the other side, on the conjugated side. So when you make the scalar product on this level, the r coordinate correspond always to level m. So the spin status that you have in level m corresponding to this wave function is exactly equal to the spin status you have here. So when you have the scalar product, you have the scalar product among the spatial components that correspond to the same level, and also the scalar product between the spin components that again correspond to the same level. So if the spin components correspond to the same level, this means the spin status is always the same. So m level may be, for instance, spin up or spin down, but you have spin down on both sides of the scalar product. So the scalar product is for sure different from zero, because you are making a scalar product within the same spin status on both sides on the of the product. So in this case, we are sure that level m on this side and level m on the other side have the same spin state. So we do not have to worry about what is that spin state, because irrespectively of the value of that state, this scalar product will be always different from zero. I made this comment concerning the spin status because the spin status is important when we discuss about the exchange term, because if we now write down the expression for this exchange term, we have phi m of r, phi k of r prime, then we have e squared divided by r minus r prime, and then we have phi k of r times phi m of r prime. If we write that, we have the double integral of d3r prime of phi m conjugated of r, phi k conjugated of r prime, then we have e squared divided by r minus r prime, then we have phi k of r, phi m of r prime. If you notice here, when we consider the r coordinate that rules the product among the wave functions, we have level m conjugated on the left side and level k non-conjugated on the other side. So when we consider these two levels that correspond to the same electron. So on one side, on the, let's say, right side of the product, we have that electron, one electron is in level K. On the other side, the same electron appears in level M. So when we make this scalar product, we have to consider, due to the fact that we have here a term that is E squared divided by R minus R prime, we may not say that, okay, those levels are orthogonal with each other and everything disappears. So we may not say that because here we have something that is not one. But when we make this product, we have that the, let's say, the spin state corresponding to level K may be in principle different from the spin state that is found in level M. So in this situation, if the spin states are not exactly the same, then this integral drops to 0. So in this case, we have to require that the spin state of level K and the spin state of level M are exactly the same. So the fact that at the same coordinate correspond on one side of the scalar product one level and on the other side of the scalar product another level introduces this requirement on the spin coordinates, because it's not said that if level K is, for instance, spin up, then level M should be spin up, or should be also spin up. So we have to require that, so to be sure that the value of this scalar product is different from 0. And just to remind an important thing, that is that here we have this minus sign. I just rewrite this minus sign here and the same minus sign here, just to recall that the result is always the same, but just to remember that it's important to have that minus sign. So the final conclusion is that in case the spin state of level K and level M is exactly the same, so both spin up or both spin down, this integral is different from 0 and is negative. So we have a negative contribution here in front of this, this term. So this means that with respect to the direct term, where the sign is positive, that can be written as the, let's say, interaction between the charge densities produced by the level M and level K. We have the exchange term that produces a negative contribution because we have the minus sign in front, and that negative contribution is observed only when the spin states of the two levels involved, the K and M, are exactly the same. And also please note that in this case, it's not possible to make use the same approach that we use here to rewrite the expression of the integral. So due to the fact that the same coordinate appears in the wave functions of two different levels, we may not rewrite this as a sort of square modulus of one level times square modulus of the other level. So this term is more complex than the other one and produces, in general, it contributes to a reduction. So contributes to a reduction of the energy of the system. The main source of this term, so the physical origin of this term, is always the Coulombian interaction, because here we have the interaction potential that we have in the Coulombian interaction. So what is the physical explanation behind the fact that always starting from the Coulombian interaction, we may obtain a contribution to the total energy of the system that is negative, not positive as we expect to have in case we have the interaction between two charges that have the same sign corresponding to the charge. The origin of that can be also related to this Kronecker delta. So it's important to remind that the spin states of the two electrons have to be the same, so to have this negative contribution, because if that is not true, then you have a 0 contribution. So nothing changes for what concerns the total energy. So the idea behind this minus sign is the following. if you have two electrons, for instance, spin up and spin down, in principle, those two electrons may stay in the same level because nothing prevents them to occupy exactly the same level. In other words, if you have two electrons that have opposite spin states, the average distance between those two electrons can drop in principle down to zero because nothing prevents those electrons to occupy exactly the same level. So the distance between those two electrons is quite small if they have an opposite spin state. On the other side, if the electrons have the same spin state, then the pole exclusion principle prevents the electron to occupy, for instance, exactly the same state, because in that case, those two electrons may not be found exactly in the same state in the system. Or in other words, if the spin state is the same, the average distance between the electrons has to be higher with respect to the case they have the same spin state. So if this is correct, then if the average distance that you have in this case, spin up, just to make an example, is larger than the average distance that you have in this case, spin up and spin down, this means that in this second case, the Coulombian interaction gives you a potential energy that is higher than in this case, because now the distance is larger and now the distance is smaller. So if you prevent the electrons to be one close to the other, then you reduce the potential energy of the system because you increase the distance between the electrons. And if you increase the distance between the electrons, the Coulombian potential term, that is this one here, is smaller because that is inversely proportional to the distance between the particles. So the fact that now we have the possibility to decrease the energy of the system comes from the fact that due to the spin state, that the spin state somehow affects also where the electron with that spin state, that spin state can or cannot go. So due to that, the spin state of the electron influences the total energy of the system, even if in the starting equations, that means in the Hamiltonian of the system, there was no contribution from the spin state. So we never wrote an Hamiltonian with the spin contribution. So that spin contribution was not there from the beginning, just appears at the end of the calculation. And is related again to the presence of the Coulombian term of the interaction potential. And also note, please note that what is the origin of the appearance of this second term? The origin of that is related to the fact that we are using as a wave function for the evaluation of the expectation value this later determinant. And this later determinant was introduced to have an overall wave function for the electrons that had the right antisymmetry properties. So the main difference between, let's say, the Hartree approach and the Hartree-Fock approach is related to this term, the exchange term, and that term is there due to the antisymmetry of the initial wave function. So the appearance of this second term is just there due to the fact that we have included the fermion behavior of the electrons. So this is let's say, a pure quantum mechanical term that appears, whose appearance, is related to the antisymmetry of the Slater determinant, so of the wave function of an electron system. Because if you remove that property, then this term disappears, so we have just the Coulombian contribution. So again, this is a pure, let's say, everything here is pure quantum mechanical, but is a pure effect of the antisymmetry of the system over this expectation value. So all these are important things to remember. So both the fact that here we may not write this just as square moduli. So here we have not the opportunity to write down square moduli of the wave functions. Then we have to remember the requirement concerning the spin state. So spin state of level k has to be equal to the spin state of level m, otherwise this integral is 0, so no contribution to the energy of the system. And to relate why here we have the appearance of the spin state, then in a very qualitative way, you may say that the contribution of the spin comes from the Pauli exclusion principle. And the Pauli exclusion principle, let's say, in a qualitative way, prevents two electrons with the same spin state to occupy, let's say, the same state, or more qualitatively, to be very close one to the other. So in this case, let's say the Pauli exclusion principle favors the reduction of the energy of the system by taking the electron with the same spin state far away from one from the other. And let's say I will better comment on this later, but this term here is at the basis of the appearance of a class of materials that are magnetic materials, because this term here gives you a possible solution for the reduction of the energy of the system. Because in principle, if all the spins of the electron were parallel with each other, then you may have a very a big negative contribution coming from this integral. So you may reduce to a great extent the energy of the system if it was possible to have all the spin states, all the electrons with the same spin state. And if you have all the electrons with the same spin state, you have a ferromagnetic system. So this term here is at the basis of ferromagnetism. Another comment is the following: if you pick up the periodic table and you choose what elements are ferromagnetic, you find that on the periodic table just a few of them are ferromagnetic. So this means that this, let's say, solution to the reduction of the energy of the system is not a solution can be easily applied. Otherwise, all the system in the periodic table would be ferromagnetic, or apart from the gases. So the idea is the appearance of this term is used to explain why some metals are ferromagnets, but this mechanism is quite hard to be used for a strong reduction, an overall reduction of the energy of the system. And this is, let's say, confirmed by the fact that in the periodic table, just a few elements are actually ferromagnetic, in particular at room temperature. So this was just a comment on the possible side, on the possible effect related to this term here. Okay, but I will comment better on that later. Yeah, okay, so it's 10 o'clock. Do you have comments or questions concerning this part?
No, thanks, I don't.
Okay, so now I stop the registration for the break, and then I will go on with the discussion after making the break.